Hello, Luke. Welcome to Lesson 34. So, today we're going to be talking about greatest common factors, otherwise known as the GCF, representing greatest common factor. Okay, and before we do that, let's just quickly review what a factor is. Hopefully, this is very easy for you. It should be at this point, but let's just run through it. We won't assume anything here. So, we've got two numbers. Let's give ourselves a 12 and an 18. If I were to ask you to find the factors for these numbers, what would you have to do? So the answer is we need to remember what a factor is. So a factor is just a number that you can use in a multiplication problem to obtain the product of the number that we want. So if the product has to be 12, what numbers can we use in a multiplication problem to get 12, right? And those numbers would be the factors of a 12. So thinking of it that way, let's just start at the smallest number, which will be a 1, and start working our way up from there. So 1 can go into 12. So 1 times 12 would be two factors for 12, because 1 times 12 is 12, right? So maybe just over here, we'll keep a tally of our factors. So we have a 1 and we have a 12. They would both be factors of a 12, right? Let's go to a 2. 2 would work also. A 2 times 6 is certainly 12. So now we have two more factors, a 2 and a 6. 3, moving right along here. 3 times 4 would also be a 12, so we can do that. And then we hit a 4. Well, we already have a 4. So 4 we don't need to worry about, right? And a 5 cannot go into 12. A 6 can, but we already have done a 6. And whenever you've reached halfway to the number, you know you can't go any further if you've started from the smallest number and worked your way up. Because obviously a 7, 7 times 1 is in 12. And if I go 7 times 2, I'm already too big. And every number after this is just going to get bigger and bigger and bigger when I multiply it by 2. So once we hit the halfway mark, we know we're done. So we've got 1, 12, 2, 6, 3, and 4. So if I kind of write those out from smallest to largest, we would say the factors for 12 are a 1, a 2, a 3, a 4, a 6, and a 12, right? So those would be, in this case, 6 factors for 12, okay? Now, if I were to do the same thing with the 18, it's the same process. So 1 times 18 would certainly be factors. So we have a 1 and an 18. And then we have, if I work my way up to a 2, 2 times 9 would be an 18. So that works. 3 times a 6 would be an 18. Right, so 3 and 6 would work. 4 doesn't work. 5 doesn't work. A 6 doesn't work. A 7 doesn't work. I'm sorry, a 6 does work, but we already did the 6. We already did the 6 up here. So 7, and then of course 8 doesn't work, and 9 does work, but we already used it up here, and now we're halfway to the 18, so we know we can stop. So we end up with the factors 1, 2, 3, 6, 9, and 18 from smallest to largest. 1, 2, 3, 6, 9, and 18, right? So those are, in this case, what do we have? 6 more factors for an 18, okay? And they're the only factors for an 18, all right? There is a limited number of factors for every number. In this case, there were 6 in both of them, all right? Now, you may remember from previous years, the next step that we might often ask is, okay, if these are the factors for these two numbers, what is the greatest common factor for these two numbers? Okay, and to understand that, we first need to remember what a common factor is. A common factor is just two factors that are shared by these two numbers, right? So where do we see the shared factors? Obviously, 1 is always going to be shared, so it's kind of trivial. We don't really care about the 1 so much. That's always going to be there, and it really doesn't help us later on at all in solving problems. So the 1, we don't really care much about the 1, but that is always going to be a common factor between any two numbers. So, of course, it'll be a common factor between 12 and 18. Next, we do have 2's in both of these, so they would be, a 2 would be a common factor. 3 is actually also a common factor. A 6 and a 4, they are not. They don't share those. Oh, I'm sorry, a 4. A 4 they don't share. So 4 is not. A 6 they do. So a 6 is also a common factor. And then they don't share a 12, and they certainly don't share a 9 and an 18. So our common factors are going to be what? They're going to be the 1, of course, 2, 3, and 6. Those are the common factors, all right, between these two numbers. Then we can move on to the greatest common factor, which is our goal in this case, the GCF, the greatest common factor, which is exactly what it sounds like it is. The greatest common factor is just looking at our common factors and saying, which one is the greatest? And in this case, it's a 6. So the greatest common factor is a 6 in this case. All right? So the greatest common factor will always be just one number, and that number is the greatest number that can go evenly into a 12 and into an 18 in this case. Okay? All right. So hopefully that was just straightforward review. Okay? Hopefully, if I gave you that 12 and that 18 and I told you find the greatest common factor, you would have already been able to do it, and probably in your head would have been able to say, oh, 12 and 18, easy. It's going to be a 6, right? 6 can go into both of those, and it's the largest thing that can go into both of those, okay? But we're going to kind of use this to kind of progress into more of an algebraic problem here. And before we do that, we're going to tie this in with what we learned, I think it was a couple lessons ago, when we talked about the prime factors. Remember, we talked about how to break a number down into its prime factors, okay? And we're going to kind of use that today. So what I'd like to do is just to redo these two problems real quick to find the greatest common factor. Only we're going to do that by means of our prime factors. Okay, so just a slightly different method here, but it's going to be the one that we will be using for our algebraic problems coming up. All right, so a 12 and an 18, we start by taking those two numbers and we're going to break them down into their prime factors. Okay, they're prime factors. Here we broke them down into all of their factors. All right, but here we're actually going to break them down into the prime ones. So if we take the 12, remember how to do this. We kind of write it as the upside down division sign, right? And we think about what prime number, starting from the smallest ones that we can think of, can go into a 12, starting with a 2 then, because a 1 doesn't really count. And remember, a prime number is just a number that's only divisible by 1 and itself. So 2 is the smallest prime number if we don't think about the 1. So the 2 is what we'll start with in this case, because we see that 2 can go into 12, right? It's an even number, so 2 can go into it. So 2 works. 2 can go into 12 6 times. We divide that out again, and this can be also divided by a 2, and that gives us a 3. And if we think about a 3, the only prime number that can go into a 3 is a 3, which would then give us 1, all right? So our prime numbers, as we've broken them down for this 12, are a 2, 2, 3, and a 1. Those would be the prime factors for a 12, okay? And, maybe let's just go ahead and do that for the 18 too. So the 18, if we find the prime factors, again, a 2 will work nicely. Now we're stuck with a 9, which means a 2 won't work, but a 3 will work. So a 3 can go into a 9 3 times, and there we go. And then the only thing that can go into a 3 is a 3. All right. Now remember, when you're all said and done here, every one of these numbers outside of this upside down division box, it should be a prime number. So watch out. If you had gone 18, let's see, 2 can go into, or let's try a 6. 6 can go into 18 3 times, and then 3 and 1. No, that's not correct, because this number is not a prime number. It's not divisible by only 1 and itself. That's divisible by a 2 and a 3. So remember, just kind of double check yourself and make sure that you did in fact only use prime numbers on the outside here. And remember, your prime numbers are, 2, 3, then you have to go up to a 5 to get to the next one, and then a 7, and then an 11, and then a 13, and then a 17, and it kind of keeps going from there. But these would be the smallest ones, and usually you're somewhere in, this range. I mean, that's usually as far as you need to go when working these problems. They're being kind of mean to you if they give you one that has a 17 as its prime factor. So anyway, it certainly could, but it's just not as nice, and they probably won't give those to you in these problems. So anyway, just make sure you understand that. That's very important. Okay, so now let's continue with the problem here. So we have our 12 and our 18 broken down into prime numbers, right? The prime factors. Now, how can we use those to get to this greatest common factor, 6? Okay, well, first thing that you might want to recognize is that these prime numbers can be used to get all of these factors for a 12. You can get all of these factors by using these prime numbers. And how do you do that? Well, certainly you could look at it and say, well, there's a 1 here. And since that's a prime factor, that's got to be a factor. And that's listed over here as a 1, obviously. There's also a 2 listed here as a prime factor. And lo and behold, a 2 is listed as a factor. So that makes sense. There's a 3 listed here. And there's also a 3 listed here. All right, so that all makes sense. But then you might say, well, what about the 4 and the 6 and the 12? Well, notice that the 4 is a combination of these prime factors. If I take the 2 and multiply it with the other 2 that's there, 2 times 2, what does that give me? That gives me 4, which is this number over here. So I can create this factor by multiplying this out, which means that I can take any combination I want here. Take whatever you want and multiply them, and that will give you a factor for 12. Okay? It doesn't matter. So I could say, okay, 2 times 2 must be a factor. Well, then 2 times 3 must be a factor. And that would be accurate. 2 times 3 is 6. That's where the 6 came from. And you say, well, maybe instead I want to take, 3 times 2, and then I'll multiply it by the other 2. I'll take 3 of these and combine them. No problem. 3 times 2 times 2. What is that? 3 times 2 is 6, times 2 is 12. Well, there's our 12. All right? So any way that you want to multiply 2 or more of these factors together, that will give you another factor. It won't give you a prime factor, but it kind of fills out our list of factors. Okay? So you can see then that these 4 prime numbers are obviously factors for 12, but they're also everything you need in order to get all of your factors. Okay? So hopefully that kind of makes sense to you. I'm going to kind of erase this a little bit. All right? So that might be the first thing to notice here when we're talking about these prime numbers, these prime factors. The next thing is, again, we're trying to get to the greatest common factor. So how do we do that? Well, to do that, we're actually going to kind of compare these 2 lists of prime numbers and pull out what's common between them. All right? You're kind of, think of it in terms of your matching socks. All right? You got to match socks from both sides. So by that I say, okay, we have a 2 here. All right, so we need to match that with another sock over here. We have to have a pair of them. All right, and we say, oh, good, we do have another 2. So great, these 2 socks, these 2 here are going to combine, and they're going to give us 1 pair of 2s. Okay, so think about what you do with socks. You take one sock and the other sock, and you bundle them together. Now you have 1 pair of socks. Right? So we take this 2 and this 2, we bundle them together, and we have 1, 2. Okay? They make 1, 2, or 1 pair of socks. All right? So don't write 2 2s. It's only 1, 2. Okay? Then we could keep going and say, okay, here's another 2. Is there another 2 over here? There's not. So I don't have another sock that I can combine with this one. So that means he is a no-go. He doesn't work for us. We can't use him to build our greatest common factor. Okay? Now let's look at the 3. Is there another 3 over here? And lo and behold, there is, right? We have a 3 here and we have a 3 here. Well, that's another pair of socks that we can combine, and that'll give us a 3. Okay, so again, it's not a 3 and a 3. We're combining each sock to get a pair of socks, which is a 1, 3. Hopefully that analogy kind of helps a little bit. All right, and then moving on, the 1, of course, the 1 can be paired with another 1. But like I said earlier, the 1s, we don't really care about the 1s, so you can completely ignore them. Don't even worry about the 1s. They're trivial. They're just pointless, all right? So the ones we do care about are the 2 and the 3 in this particular case. All right. So we've gone through all of our individual socks over here, and we haven't found any other pairs. So that means this little lonely sock over here, he's a mismatch. He's a mismatch, and this 2 over here, he's a mismatch. They don't have a pair, so we can just ignore them. We throw them away. They're useless to us. Okay. They don't make a pair anymore. Now we come down to our pairs of socks down here, and to find the greatest common factor, we are now going to, what color did I use? We're going to multiply these two because they're factors. So we're going to multiply them by each other since they're factors and find out what the product is. So 2 times 3 is 6. And that is our greatest common factor. Okay, there it is. So it's kind of fun if you like sorting socks. Okay. So yeah, here we go. It matches over here. Okay. So let's just try maybe another one here just to make sure that we understand how that is working. And then we'll move on to the guts of our lesson today. So let's go here and I'm going to give you maybe 2 more numbers here. Let's go with, well, we'll put them in black, I guess. Let's go with the numbers. Oh, I don't know. Let's go 64 and 28, maybe? I don't know. I'm making these numbers up, so we'll see how these work out. So if we have these as our number, and we're trying to find the greatest common factor, okay, is what? Okay, so to figure that out, we're first going to break these down into their prime numbers, their prime factors, right? So we can divide this by a 2. That'll give me 32. I can divide it by 2 again. That's 16. Divided by 2 again. That's 8. Divided by 2 again. That's 4. Divided by 2 again. That's a 2. And, of course, I could go one more if I want to bring it down to a 1. All right. Wow. A lot of 2's there as our factors. Over here, what have we got? Well, we've got a 2. That'll be 14. I've got another 2. That would be 7. Now, a 7 is a prime number. The only thing that can go into it is itself. So 7 would give us 1. All right. So we don't have as many over on the 28 side. Now we have to match socks. So what do we have? Well, I've got a 2 here and a 2 here. So that'll give me 1, 2, right? And I'll put my multiplication sign because it's a factor. And then I'm going to have, what else do I have? I have another 2 and another 2. So I have a set of 2's here. So I can multiply that by another 2. It's another pair. All right. Then if you look down the list, all I have left over here are 2's. If we don't care about the 1, we ignore him. And I don't have any more 2's over here. And over here I have a 7, and I don't have any 7's over here. So those are the only things that are in common between these two numbers. So our greatest common factor then is 2 times 2, which is 4. That is our greatest common factor for the numbers 64 and 28. All right? So hopefully you see how nice that was. That would have been maybe a little bit more difficult if you were trying to do it the other way. If I had said, okay, what's the greatest common factor between 64 and 28? And you would have had to write out all of the factors for 64, and then all of the factors for 28, and then look at the common ones, and then find the greatest common one, and finally realize that it's a 4. This is a much faster way to do it. Okay? Great. Okay, now let's take what we've reviewed here and apply it towards more of an algebraic expression. So let's say that I have an algebraic expression such as 3x squared y plus, well, I won't even put the plus here. I'll just say 3x squared y, and I will say my other term is going to be a 12 x to the 4th y to the 3rd. Okay, now here just think of these as kind of numbers, just like we were looking at the other two numbers. And if I were to ask you what's the greatest common factor between these two terms, you might be kind of scratching your head and going, well, I don't know, I'm lost, how is that going to work? Well, it's pretty straightforward. We just have we have letters here, and that kind of throws us off, but it's not complicated. So let's start by just looking at the numbers, okay? We have a 3 and we have a 12. So kind of ignoring the letters for the moment, let's look at the 3 and the 12 and find the greatest common factor between a 3 and a 12. Now, these two are pretty simple. We could certainly, factor them out over here, but obviously, I think you can do this one in your head if you're to, factor them out. The obvious thing is that the greatest common factor between a 3 and a 12 is going to be a 3, right? So, therefore, we write the 3 as the greatest common factor for these two numbers, all right? But the letters are the part that maybe is a little more complicated and maybe might confuse you. But let's take a look at it. What does x squared y mean? Okay. Well, another way to write that would be, write this whole term, would be 3 times x times y, right? X squared is just meaning x times x. So I'm just kind of eliminating the exponents by spreading everything out. 3 times x times y. Over here, I'd have 12. Now, I'm going to just write that as its prime factors over here. That would be a 2 times a 2 times a 3 times an x times an x times an x times an x, 4 x's, right? And then I have to multiply that by 3 y's. Y, and y. All right? Okay, so that's kind of just spreading it out, writing it long form, okay, as a list of prime factors and then all of the factors of the x to the fourth and y to the third, okay? Once I get it down to this, now I can actually find my common ones here, okay? And this is kind of redoing, I guess, what we already did in our heads with this 3. So clearly we can see here that if we kind of match our socks, we have a 3 and we have a 3. That's how we got this 3 here, right? But now we can match other things too. We can match some variables as well. Let's start, matching some more socks here. So I've got an x here and I've got an x here. Well, then I can put another x or a x down here. That's one matched sock, all right? Then I can look for other ones, and I can say, okay, I have a second x here, and I actually have a second x here. So that would make another x down here in my greatest common factor. Next, I have a y in this one, and lo and behold, I do have a y way down here in the other one. So I can multiply it by a y. Now, I've used everything on this term, so there's nothing else I can do. Over here, then, all of these other leftover pieces, they're just kind of the mismatches. They don't have any pairs, anything in common with this other term. So our final greatest common factor number is going to be a 3 times x times y. That is going to be 3x squared y. So that is our greatest common factor. Okay, so it's pretty straightforward. Basically, we're just writing the numbers as their list of prime factors, right? And then we write all of our variables, our letters here, in the long way. Spread them out. X times y. The whole way. And then we're taking the greatest prime factor between the numbers. And then essentially what we're doing here is we're saying, okay, this has an x, this has an x, so we do know there's an x down here. It's x to the second power, it's x to the fourth power. We take the most that we can such that they're common to both. All right, so the most we can take from here would be a 2 because this one can handle a 2. This one can handle no more than a 2. So we can't take more than 2 away from this one, but we can take 2, and we can also take that 2 from the 4. That's totally fine. It's got enough. So we end up with this x to the second, okay? That's the most that we can take is 2 x's. The y's, this one has a y to the 1, right? And this one has a y to the 3. What's the most we can take away is a 1. That would be common to both. So it would be a 1, y to the 1, okay? Does that make sense? Good. So let's try some problems here and see how we do. So kind of backing up to here. Now we're kind of getting into the meat of our lesson for today. So let's take a look at this problem. It's an expression, and what I want you to do is find the greatest common factor between the two terms in this expression. All right. I know there's addition here. All we're doing, though, is thinking of this as two expressions, and I just want to know what's the greatest common factor between these, between these two, excuse me. All right, so what I want you to do is just to look at this expression and try to find the greatest common factor between these two terms. Okay, I know there's addition here, but I want you to just kind of ignore the addition for right now and focus in on each of these two terms and find the greatest common factor for these two terms. Okay, so we'll do this one together, and basically let's write this 4 as a list of prime factors. Now, 4 is a small enough number that you should be able to do it in your head. It's going to be a 2 times a 2. That's the two, prime factors for a 4. Then we have x squared, so we'll say times x, and then we have y to the third, y times y times y, and then we have a z, and then we have a p, right? And then our second term, just separate them with this plus sign, is an 8. Well, let's think about what an 8 is. An 8 is going to be a 2, and that would give me a 4. And I do another 2, and that would give me a 2. So it's going to be 2 times 2 times 2, right? You just double check that. 2 times 2 is 4. 4 times 2 is 8, right? So those would be our list of prime factors. Then we have x to the third. Well, that's just, x times x times x. Y to the second is just y times y. And then we have a z. Okay. So it gets really long when you start doing this. Make sure you have room on your page. All right, so now let's combine. Let's match some socks. So we've got a 2 here, and we have a 2 here. So we put a 2 for our greatest common factor. We have another 2 here. We have another 2 here. So we can put another 2 for our greatest common factor. Now here, I might just say I've got, 2 x's, and I've got 2 x's over here. They work. So I'm going to have 2 x's, right? And then I've got, for y's, I've got, 3 y's over here, and I've got 2 y's over here, so I can take, 2 y's out. I can match those individuals. So I end up with y times y, right? 2 y's. And then I have leftover y, but there isn't another y over here. I have a z, and that can combine with this z over here, or match, I should say, with that z. So we have a z in our greatest common factor. This one has a p, but this one has not even one p, which is fine. It just means it's a mismatch. There's nothing that it can match with. So our greatest common factor then is 2 times 2, which is 4, x times x, which is x squared, y times y, which is y squared, and z by itself. This would be our greatest common factor. Okay? So hopefully that didn't pose a problem to you. It's pretty straightforward. And a lot of this, we're going to kind of begin to do it mostly in our heads as we go here. So I'm just going to kind of erase this so we have a little bit more room for this next problem. Let's try this one. So, a little bit bigger. Here, let's try to do maybe a little bit more in our heads. Let's start with this term and break it down. Well, actually, you know what? Let's see how much we can do in our heads. Let's look at just the numbers. So we have a 3, we have a 9, and we have an 18. 3 numbers. And we have to find the greatest common factor between those 3 numbers. Now, 3 is a pretty small number. The greatest factor for a 3 is 3. Nothing larger than 3 can go into 3. So maybe right off the bat, we'll just say, can 3 go into these 3 numbers? Well, 3 can go into a 9, 3 can go into an 18. And since 3 is the largest number that can go into a 3, the greatest common factor for those is going to be a 3, right? That's the greatest number that can go into all 3 of those numbers. Now let's look at the a to the 4th. So I have an a to the 4th. Here I have an a to the 3rd. And here I have just an a. So remember, we have to pull out the most that we can from these terms. So I could pull out a 1 here. That's the most I could pull out, would be a 1. And because that's the most, and they all have an a, then a is what we would pull out, right? So we have to pull out the most that we can such that it's common to all 3 terms. So a to the 1 is common to all three terms. They all have at least one a, so we can pull out the a. I can't pull out an a to the 3 because this one does not have an a to the 3. It only has an a to a 1. So a to the 3 is not common between these three terms, right? So the most we can pull out is an a. All right. Then let's go on to the b. So if I have a b, here I have a b squared, here I have a b to the 4th, here I have a b to the 3rd. So I've got the squared, I've got the 3rd, and I've got the 4th, right? So what is the most that's common between these three terms? Well, it would be b squared, right? It's the smallest of the three numbers because that's the most that's common between these three, okay? So we end up with times of b squared, okay? Now we go on to the next one here. Let's look at c to the 10th. Well, c to the 10th is here. There is a c here, and there is a c here. So that's good. C's are common to all three terms. But now we need to figure out how many of the c's are common. Well, this one has 10, this one has 4, and this one has 6. So the most that's common is 4, right? So the c to the 4th is what we'd put into our GCF. And then finally, we have the f at the end here. So we have an f here, we have an f squared here, we have an f to the 3rd here. So what's the most I can pull out? In this case, it's f to the 1. Okay, or just f if you want. Okay, very good. And then we're out of variables over here. So we've used all of these. So nothing else could possibly be common. And in this case, we've actually used everything and all of them. So this is our greatest common factor. But let's just, write it a little nicer. It's going to be 3 times a times b squared times c to the 4th times an f. This is our greatest common factor. Okay, good. Let's try a couple more here. This is just take some practice here. So 5, 30, and 25. What is the greatest common factor between just the numbers? Just kind of focusing in on the numbers. 5, 30, and 25. Well, this one is similar to the last problem, right? If we look at our smallest number, that's a 5. And that's a prime number. The only number that can go into a 5 is a 5. So we better hope that 5 can go into these ones as well. And as it turns out, yes, it does. 5 does go into 30. 5 does go into 25. So, therefore, our greatest common factor is going to have a 5, right? Okay. Then we have a squared. All right, so we have a squared. We have an a to the 4th. We have another a squared. So we have a 2, a 4, and a 2. We can pull out a 2. So we have 5a squared. B to the 3rd. This one doesn't have a b at all. So the b to the 3rd, he's a mismatch. Can't do anything with him. Don't write a b down here because b is not common to all three terms. It's common to this term, but it's not common to the 3rd term, and it has to be common to all three. All right? So we just get rid of him. He's a mismatch. Then we have a c. This has a c, this term has a c, and this term has a c. So we can say, all right, great. We know there's a c, but how many? Well, I've got a 1, and I've got a 2, and I've got a 6. So 1 is the most that I can pull out that would be common to all three. So we end up with just a c. So the greatest common factor is 5a squared c. Okay. All right, let's try the next one. Now, this next one is designed to be a little bit trickier. We've got bigger numbers here, right? 48, 84, and 36. It might not be obvious right away what would be the greatest common factor for those three. So in this case, let's actually figure that out by stepping through the process of finding the prime factors. So we have a 48. Let's break that down. That would be divisible by a 2. Which would give us 24. That's divisible by a 2, which would give me a 12. That's divisible by a 2, gives me 6, by a 2, which would give me 3. 3 is a prime number, so we can stop there. Then the 84, another big number. Divisible by 2 again, it's an even number. So 2 can go into 84 42 times. 2 can go into 42 21 times. Now a 2 can't go into 21. So let's go to the next number, the next prime number, which is a 3. Can 3 go into 21? Yes, it can. So 3 can go into 21 7 times. 7 is a prime number, so we stop there. Then we have a 36. And that's divisible by a 2. By a 2 again. and then again by a 3. Okay, so now we have all of our prime factors. And now again, to discern what is the greatest common factor down here, we need to just match some socks. So we have a 2 and a 2 and a 2. So we know that a 2 will be a common factor. And we have another 2. They all have another 2. So we can throw in another 2, right? They don't all have another 2, so that one's not going to work. Obviously, the next 2 isn't going to work. They do all have a 3, though. So we can throw in a 3, right? So that is going to comprise the greatest common factor for these 3 numbers. 2 times 2 is 4, times 3 is 12. So 12 is the greatest number that can go into 48 and 84 and 36. All right? So now we have the number out of the way. Let's look at the rest of it here. So we've got x squared. We do have an x, and we do have an x. So how many can we take out? Well, we have a 2 and a 3 and a 3. So the most we can take out is a 2. So we have x squared. And then what else do we have? We have a y and a y and a y. And they each have a 3, a 6, and a 5, respectively. So what's the most we can pull out? It's going to be a y to the third. And then finally, we have the z. And the z, we have 1 z, we have 2 z's, and we have 3 z's, or 7 z's. The most we can pull out would be 1 z. So we end up with just a z. Now we can just kind of make this look nice. 2 times 2 times 3 is 12. So we end up with 12 x squared y cubed z. Right? That would be our greatest common factor. All right. Excellent. One last one here, just for fun, okay? So this one, I've actually selected some pretty large numbers here. So let's, do the same thing we did before. And actually, you know what? Let's pause the video and try this one on your own first, and then we'll do it together. All right, so let's see how you did with these large numbers here. So the first step is going to be to try to factor into prime numbers the three numbers here, 104, 312, and 234. Big numbers. All right, that'd be very difficult to do the old way of finding all the factors. So let's start with 104. And you're going to get really good at this eventually, right? 2 can go into this, let's see here, 26 times to 13. And 13 is a prime number, isn't it? Yep, it's only divisible by 1 in itself. So big number, 104, but it only has 4 prime numbers to it. So that's kind of nice. All right, let's do the 312. So 312, that's an even number, so 2 can go into it. Let's see, 2 can go into 31. Well, 15 times with a remainder of 1, which would make this a 12. 2 can go into 12 6 times, so it's 156. It's an even number. 2 can go into 15 7 times, which would give us a remainder of 1, which would make this a 16. 8 times. 2 can go into this 3 times with a remainder of 1, which gives this 18. 9 times. And then a 3. 3 can go into this, right? And if you weren't sure, remember the rule. 3 plus 9 is 12. And 3 can go into 12. So 3 can go into 39. All right, so 3 can go into 39 13 times. And look at that. That's the same over here. 13 is a prime number, so we stop there. All right, let's try 234. So 2 can go into that. Let's see, once, and 7 times. Okay, and then this one, 2 cannot go into it. But again, remember the rule for the 3s. 7 plus 1 plus 1 is 9, and 3 can go into 9. So 3 can go into this number. 3 can go into 11 3 times with a remainder of 2, which would make this a 27. 3 can go into 27 9 times. This again is divisible by 3 because 3 plus 9 is 12, and 3 can go into 12. So 3 can go into 39 once and 3 times, so we're left with another 13. Excellent. So Now let's try to find the greatest common factor. So let's match some socks. Let's see. They all have 2's, right? So a 2 will be the greatest common factor, or at least part of it. And then we've got more 2's here, but this one doesn't have any more 2's, so that won't work. This one has a 2, which doesn't work, a 2, which doesn't work. It has a 13. This one has a 13, and this one has a 13. They all have that 13, so 13 is going to be in here. And we've used everything in here, or crossed it out. And so therefore, we're done. So the only two numbers that are common for all of these prime factors is a 2 and a 13. So that'll comprise our greatest common factor. Okay, so we have 2 times 13. Now we have to hit the variables. So this one has a k, this one has a k, this one has a k. So we know a k is going to be in here. To what power? Well, we have a 2, we have a 4, and a 6. So the most we can pull out is a 2, because that's the most that'll fit into all three of those. And then we have a p, and we have a p, and we have a p. So we know there's going to be a p. To what power? Well, we have a 4, we have a 2, and a 2. So it's going to be a 2, right? Lastly, we can just multiply this out. 2 times 13 is 26. K squared p squared. So that is our greatest common factor. All right, so hopefully you kind of had some fun with those. They're not difficult, and it's just a lot of simple computations. It can be kind of fun, I think, going through there and matching all those socks and coming up with the greatest common factor. So we will stop it here, and in a couple lessons from now, we will kind of get back to this and start using this for another process in algebra.